Alan, you have shown how through inflation theory, the universe can be generated with its incredible amount of matter and energy from virtually nothing, but not quite nothing. Maybe you
That's
need
correct.
1 gram, you need some laws of physics. The ultimate question, philosophers normally ask it, not even theologians, but philosophers, is why is there anything? Why is there something rather than nothing? How do we begin to even think about that?
Right. Not very well, I should maybe say, to start with. I think it's a hard question that we're only beginning to scratch the surface of. I think the only thing that physicists can really say about that intelligently is not a complete answer to the question, even if it's right. But we can suppose that the laws of physics somehow exist before any universe exists. And I think we need to make that assumption before we can say anything. And where those laws of physics come from, as far as I can tell, physicists do not at the present time have even a clue. It's not a question that we even know how to approach. We might hope someday to try to answer it. I'm not saying it's beyond the range of science, but I think it's completely beyond the range of any ideas that are prevalent now.
Okay, but let's look at the pieces. What literally do you need to begin a universe? Because we actually need today, after the work that you and your colleagues have done, a lot less.
That's right.
Than we needed before.
That's
so
right. That's
contrast that for me.
That's right. Okay. Well, inflation does go a long way towards the possibility of thinking about a universe literally created from nothing. One does have to presuppose, as I said, that the laws of physics already exist. Then I think one interesting way to think about this question, which makes it look like we're almost there, but it's a little bit deceptive, is to think about it simply in terms of conservation laws of physics. There are a number of quantities in physics that we believe are conserved. Total energy we believe is conserved. Total charge we believe is conserved. Total angular momentum we believe is conserved. We used to believe that a total of something called baryon number is conserved, where baryon number is positive for matter and negative for antimatter. Mm-hmm. So you had to produce matter and antimatter always in pairs. If we look at the universe today, we might ask ourselves whether any of these conserved quantities are non-zero. If they were non-zero, it would mean that you could not produce a universe from nothing consistent with those laws of physics. You might hope to find different laws of physics some other time, but if we assume the laws of physics have these conservation laws, then if you start with nothing, you better have nothing at the end, because that's what a conservation law means. So it pays to look at each one of these conservation laws. We now believe that everything is okay as far as the possibility of producing a universe from nothing, as far as our conservation laws are concerned. Total charge was never a problem. The total charge of our observed universe, so far as we can tell, is consistent with being zero. Total angular momentum is also not a problem. If we look around the universe, the total angular momentum we believe is consistent with zero. We do see individual galaxies, of course, spinning, but they spin in all different directions, and people have tried to add up all of those spins, and as far as we can tell, it's zero, like it ought to be. Total baryon number is a little bit more problematic. We don't know for absolute sure, but we have reasons to believe that all the stuff out there is like the stuff that's near here, which is essentially all matter, not antimatter. There may be some antimatter in cosmic rays that's produced by collisions and things. We'd expect that, but by and large, we think we live in a universe of all matter. However, we no longer believe that baryon number is exactly conserved. So we now have perfectly consistent theories, consistent with everything that we know, which allow for the possibility that this net baryon number of the universe, the excess of matter over antimatter, was actually created by dynamical processes in the early universe. So that seems to be okay. Finally, we have energy. I think it's the only thing I haven't mentioned yet.
That's the big one.
That's the big one. Where does the energy of the universe come from?
That's all the matter. Through E equals MC
That's right.
squared.
E equals MC squared. So energy and matter are the same.
Right.
There's a lot of matter out there. The key fact, however, is that energies are not always positive. There are negative contributions to the total energy of any system in principle. And in particular, gravitational fields actually have a negative energy density. And for the universe that we observe, it actually is consistent to believe that the total energy of all the stars and galaxies, which by E equals mc squared is a fantastic amount of energy, that all of that energy is canceled exactly by the negative contribution of the gravitational field that exists throughout the universe and fills it, really. So the total energy of our universe is consistent with being zero. So with all conserved quantities being equal to zero, it's then conceivable within the laws of physics that we know for the universe to be created by literally nothing. But that doesn't mean we yet understand the process.
Well, inflation, your creation, is the key element that shows how that can happen, how all of the matter, energy, density of the universe could have been created from that laws of physics, an extremely small amount of matter through the inflationary process, and then the decay of that has the spewing out of all these hot particles and energy and matter, and some of them cancel, and what's left over becomes the Big Bang, and everything happens. So you start from almost nothing, and you create this enormity of what's the ratio between what you start with and what you end up with?
Perhaps 10 to the 75, could be more. 10 to the 75 is kind of the minimum.
Wow. So whatever you saw, 10 to the 75th power of energy density you've created through inflation.
That's right.
And so you are getting enormities of something from virtually nothing.
That's right. And even that would not be possible if it weren't for what I previously said about the conservation laws.
Right, sure, right? Sure, because as these
you could never have enough of, if anything was non-zero, you could never have enough of it existing before inflation for inflation to do its job.
Right. And so you have this enormity from virtually nothing, but it's not quite nothing.
Well, this is certainly not a question that physics has a definite answer to, as you might guess. I think the only context in which physicists can say anything here that I think is relevant is if we are just willing to assume that the laws of physics existed before there was any kind of a universe. If you ask us where did the laws of physics come from, right now I think physics doesn't really have any clue about where the laws of physics came from. I would not want to go so far as to say that it's a question beyond the range of science. I think someday we may have a clue. But if you ask where we are now, I think the honest answer is we don't have a clue. But if we assume that the laws of physics already existed before the universe did, then we can talk about at least speculative theories that actually describe how the universe itself was created from nothing. Now, I should maybe clarify here that nothing does not mean empty space. In the context of general relativity, space was maybe just empty before general relativity, but in the context of general relativity, empty space is malleable. It can bend, it can twist, it can stretch. So empty space is already stuff, in the real sense of the word stuff. So nothingness really means something that's the complete absence of space, and presumably also the absence of time. It's a very abstract concept of nothingness. But one can maybe imagine, we don't have a solid theory of this, one can maybe imagine that before the universe there was nothingness in this sense. It's hard to even know for sure if the word before is applicable here, since I just told you time did not exist. But one could talk about theories in which one tries to describe the creation of the universe out of nothingness as some kind of a quantum transition. And certainly papers have been published about that. It is a topic that physicists do speculate about. They do publish papers about it. But it's certainly not a topic about which there's any general agreement at the present time.
But even in those theories, you do need some laws of physics to start with.
That is correct. Even in those theories, one does need laws of physics to start with. If one does not assume that, I don't think physicists have anything to say at the present time.